Length contraction. Remember in the previous lecture we talked about time dilation. The proper time is measured by an observer with respect to whom the event occurs at the same point in space, and an observer that is moving with respect to the proper reference frame will measure slower clock. So the delta t will be gamma times delta tp. Gamma is our relativistic correction factor. Now, how about the length measured by these two observers? The proper length of an object is the length measured by an observer at rest relative to the object. So that's the observer that is measuring the proper length. So if we have an observer moving relative to an object, this person always measures a length less than the proper length. This effect is known as length contraction. And the stars are at rest with respect to Earth approximately. So we can take approximate reference frames that are at rest with respect to an object or a length. Okay, so let's think about this experiment. We have a spaceship that is moving with velocity v in the j-hat direction from one star to another star. So as I said, these stars are at rest with respect to the Earth. Therefore, if we ask who is going to measure the proper length, the Earth observer who sees the stars at rest will measure the proper length. Who is going to measure the proper time? In the reference frame of the spaceship, the starting point is the same, the end point in the spaceship is the same. So therefore, the spaceship observer measures the proper time. Okay, and the distance delta y measured by the spaceship observer will be v, the speed of the spaceship multiplied by the proper time. How about the time interval measured by the Earth observer? Well, the Earth observer is measuring the proper length, Lp, the distance between two stars at rest. Lp divided by the speed of the spaceship v is basically the time measured by the Earth observer. Because the spaceship observer is measuring the proper time multiplied by gamma due to time dilation effect is the time interval measured by the Earth observer. So we can see that Lp will be equal to gamma times v times delta Tp. Okay, the length measured by the spaceship observer, so this delta y is the length measured by the spaceship observer, is v times delta Tp. For v times delta Tp, we can substitute L, the length measured by the spaceship observer. So we see that the proper length is gamma times L, or L, the length measured by the spaceship observer, is the proper length divided by gamma. Remember, gamma is greater than or equal to 1. So gamma is 1 over square root 1 minus v square over c square. So if we substitute here, it will be the proper length multiplied by square root 1 minus v square over c square. So the length measured by the spaceship observer is less than the proper length between the two stars, the proper distance between the two stars. Okay. Now, if an object has a proper length L sub p, its length L, when it moves with a speed v in a direction parallel to L, appears shorter. How much? Shorter by a factor of gamma. So 1 over gamma is our factor here, correction factor for the relativistic effect. Okay, so this is our length contraction. For example, if we have a meter stick that is measured by an observer in a frame attached to the meter stick. So this meter stick is at rest with respect to an observer that we put on this meter stick. This observer, because the two ends are at rest, will measure the proper length. If the meter stick starts moving with a relative velocity v with respect to the lab frame, a meter stick measured by an observer in a frame in which the stick has a velocity relative to the frame is measured to be shorter. How much? The proper length divided by gamma. So the lab frame observer, because sees the two ends moving, will measure a length that is LP divided by gamma. Okay, so this is the length contraction effect. Now, let's take a look at an example. An astronaut takes a trip to Sirius, which is located a distance of 8 light years from the Earth. The astronaut measures the time of one-way journey to be 6 years. If the spaceship moves at a constant speed of 0.8 times the speed of light, how can the 8 light years distance be reconciled with the 6-year trip measured by the astronaut? Who is measuring the proper length? A trip from Earth to Sirius, so Earth and Sirius are at rest with respect to the Earth observer, so 8 light years is the proper length measured by the Earth observer. So the proper length is the proper distance, that is 8 light years. So, because the astronaut is basically moving from Sirius to Earth, the length measured by the astronaut will be relativistically corrected. It's going to be the proper length divided by gamma, the relativistic correction factor. So this is 8 times square root of 1 minus v square over c square, 1 minus 0.64. So that will be 4.8 light years. On the other hand, who is measuring the proper time? The end point and the start point are the same for the astronaut. The astronaut is remaining in the spaceship, so the time interval between two events occurring at the same point in space is the proper time interval. So delta Tp, he will measure, will be the length he measures divided by the speed v. So 4.8 light years is the length seen by the astronaut, the distance seen by the astronaut, divided by 0.8 c. The time of travel will appear to be 6 years. Okay, so for the astronaut, one-way journey will take 6 years. So this can be understood. Now, but if this trip is observed with a powerful telescope by a technician in mission control on Earth, at what time will the technician see that the astronaut has arrived at Sirius? Okay, so with respect to the Earth observer, how long does it take to reach Sirius? Delta T, that's the proper length LP that the Earth observer measures divided by V. So it's going to be 8 light years divided by 0.8 c. So that's going to make 10 years. But however, if we have an observer that is trying to detect the arrival of the astronaut in Sirius, plus light has to travel from Sirius to Earth to the telescope. All right. And how long will it take? The time it will take is the proper length LP divided by the speed of light, because now it's the light that is traveling. So we have 8 light years proper distance divided by c, that will take 8 years. So the detection will occur in 10 plus 8, 18 years. So the technician sees the arrival in 18 years. Okay, because now we're looking for light that comes from Sirius to the telescope, which is going to tell us that this person has arrived in Sirius. So the answer will be 18 years. Okay, to summarize, the proper time is measured by an observer who sees this event occur at the same point in space in that reference frame. The reference frame that is moving with a relative velocity v with respect to the proper proper frame will measure time dilation. Delta t will appear larger, gamma times delta tp. The moving clock will appear to run slower. The proper length of an object is measured by an observer who is at rest with respect to the object. So the two endpoints should be at rest. If we have an observer that is moving relative to an object, this length will appear to be shorter, and the effect is known as length contraction. It is the proper length divided by gamma, or proper length multiplied by square root 1 minus v square over c square. So here we have to be careful about the direction of motion. You see the direction, the relative motion of the two reference frames, S prime and S frame, should be in the direction in which the length is measured. So if we move perpendicular to this meter stick, we would measure also the proper length in the other reference frame, because the length contraction is only on the x-axis. All right. Then we talked about a voyage to Sirius example. An astronaut takes a trip to Sirius. Who is measuring the proper length? The Earth observer sees the Sirius and Earth at rest, so approximately. So 8 light years is the proper length. The length measured by the astronaut is length that is contracted by the relativistic correction factor, 4.8 light years. The proper time interval is measured by the astronaut because the end point and start point are within the ship, so we have the same point in space. Therefore, we measure the length measured by the astronaut divided by the speed, 6 years. So this explains how we have a 6-year trip time measured by the astronaut. On the other hand, if we look at the time it takes to reach Sirius, that's the proper length divided by v, that's 10 years. And if we ask ourselves, we have a technician who is looking at a telescope to try to measure, try to detect the arrival at Sirius, then we need to have light come from Sirius to the telescope, so that will be the proper length divided by c, an additional 8 years, so it will take 18 years for the technician to see the arrival.